4. Sampling distributions. In the first part of this lectures we learned that there are two main types of problems on normal probability distribution of the target population. The first type is on finding the area under the distribution curve on some z-score interval with given endpoints. These problems are solved with the help of the cumulative normal distribution. The second type is the problem where the area under the curve is known and it is required to find the endpoint or endpoints of the z-score interval. These problems are solved with the help of the inverse normal distribution. After we learned the central limit theorem, we understood that we can apply the same methods not only for solving the problems on normal probability distribution of target populations but also for solving similar problems for big enough samples from the populations with arbitrary distributions. The difference is that now we must use not the standard deviation sigma of the population, but sigma over the square root of the sample size. To demonstrate this approach, let us solve the problem. A population has a mean of 50 and a standard deviation of 19. If a random sample of size 59 is taken, what is the probability that the sample mean is? A. Greater than 50. B. Less than 54. C. Between 48.5 and 54.5. The endpoints are given and you are required to find the area/probability here. The only difference compared to the problems with populations is that you need the sample size now, which changes standard normal deviation from 19 to 19 over square root of 59. So, instead of typing 19 into the standard deviation cell, you type equal 19 over square root of 59. Do not forget to type in sing equal and click enter in the end of the expression. The answers are 0.9471, 0.5, and 0.6934. The same results you get using Colab 4, cells 11, 12, 13. Solving problems with the inverse function is also similar for populations and big samples. Let us say that you are taking samples of size 50 many times from the population with mean equals 100 and STD equals 10. It is known that 90% of times the average value of the samples is less than some value x. Find this x. To solve the problem, use book 4 as you would with the regular normal distribution. Bu instead of typing 10 into the cell for the standard normal distribution, type there equal 10 over square root of 50. The answer is x equals 101.8. Colab 4, cell 14 gives the same result. When the size of the sample is comparable with the size of the population, 5% or more, and the sampling was performed without replacement, then the standard deviation of the sample average is not equal to the sigma over the square root of n. It should be multiplied by the correction factor equal to the square root of n capital minus n lowercase over n capital minus 1, where n capital is the size of the population. For example, a population of size 250 has a mean of 35.6 and a standard deviation of 4.89. What is the probability that the average value of 100 elements of the population is greater than 36? To solve this problem, use book 4 or Colab 4, cell 12, as you did previously, but additionally to the inputs 35.6, 4.89, 36, and 100, take into account correction factor for standard deviation. It will change the answer to the problem to 0.14 from 0.21. The last type of problems discussed in this video is about controlling the manufacturing process. The input includes the data series, which is the number of units produced per minute. The goal is to keep this function approximately constant, so the input also includes the desired mean and standard deviation. In book 4 I've implemented 3 Nelson's rules when the current reading is considered as out-of-control reading. Rule 1. The point is more than 3 standard deviations away from the mean. Rule 2. It is one of 9, or more, points in a row that are on the same side of the mean. Rule 5. It is one of 2 or of 3 points that are more than 2 standard deviations away from the mean in the same direction and belongs to the trio of consecutive points. Run the code. Each of the out-of-control points is reported and shown at the graph. Points corresponding to the first rule are shown in the red color, to the second, in pink, and to the fifth, in blue. To start the application, copy and paste the array of data, enter the desired mean, in this. Example 20 and the desired standard deviation, in this example 2.1. Click enter and see that out-of-control points are detected. Add more input data, for example, points 34 and 15. Click enter. You see that 34 is out of control, while 15 is not.